So on to part 3 of our few words about waves, although at this point you may be thinking it's a little more than a few words. What we need to do that now, though, this is really the last part of our 3 parts here. We want to talk about 3 key facts about the speed of waves. Before we do that, though, just as an aside, in the last video clip, offhand, I mentioned Picasso. It's interesting for those of you who are fascinated by art history, things like that Einstein and Picasso were contemporaries. In fact, there's a book, for those of you interested perhaps, called Einstein, Picasso by Arthur I. Miller. That you might want to check it out, see what it's all about. The subtitle is Space, Time, and the Beauty That Causes Havoc. So it sort of puts them side by side, looks at their life and their work together and draws some parallels and things like that. So Arthur I. Miller, Einstein, Picasso, I just happened to be thinking about that since I mentioned Picasso offhand last time. Maybe that's why I did subconsciously. I was thinking about that. I'm not sure, but there you go. Einstein, Picasso, Arthur I. Miller. As you may know, there are dozens, hundreds of books on Einstein out there, and many of them are very good. So you can explore that. Later on in the course, we'll talk about the end, some books to continue on with in terms of Einstein if you're interested in pursuing it more. But now we're on to a few more words about waves. Part 3, key facts about the speed of waves. I think I mentioned this in an earlier video clip, but just to make sure, we're using speed and velocity interchangeably. For those of you who've had a little physics, you know technically there's a difference between velocity, the concept of velocity, and speed being the magnitude of velocity. Velocity having a direction as well as a magnitude. So again, we're not going to have to be too concerned about those exact definitions. So we'll say speed of waves, velocity of waves, speed of light, the velocity of light will be meaning the same thing. Okay, so 3 key facts. Number 1 key fact is the speed depends on the medium. So what do we mean by that? Well, consider waterways. Again, maybe we have a long tank. We're going to generate some waves in this tank with our hand or some sort of paddle device. If we replace the water in the tank with another type of fluid, another liquid that had different properties, in particular had maybe different viscosity, different density, the speed of the waves we can generate is going to be different compared to the water. At a certain point, if you have molasses in there, you can't generate really waves at all, or they'll die out almost immediately. But the idea being is that the speed of waves, this pattern disturbance propagating through a medium, is going to change depending on the medium itself. Another example would be vibrations, which a wave-like phenomenon in a steel bar or something like that. The more rigid the steel bar is, the faster the waves are going to travel, everything else being equal. If it's a softer type of bar or whatever, then the waves are not going to travel as fast. So, key point, the speed of the waves depends on the medium. Second point is, if we have a moving source, we're going to add on to this in a second here. What do we mean by moving source? Well, again, go back to the idea of a tank, long tank of water maybe, and we have a paddle device or a hand. We're going to generate waves by just moving it up and down. And one key thing to remember, I mentioned this actually I think in part 1 of the video clip, but to remind ourselves here is that when we're talking about, if we have this paddle device and we're generating waves and they're traveling down our tank or through our bathtub or swimming pool or whatever it happens to be, the water molecules themselves are not moving with the waves. The wave that's traveling is a pattern or disturbance within the medium, which is the water in this case. The actual water molecules are moving up and down in that peak and trough. So say we've got some water right here. I start generating my waves. So the water molecules at this point, as a peak comes, they're going to move up. and then the trough, they're going to move down, and then up and down. So the water molecules are moving up and down, and the wave pattern is traveling that way. So we're not actually talking about the speed of whatever the medium is composed of as it's moving through. It's the speed of the pattern or disturbance moving through the medium. So then when we have a moving source here, okay, so I've got my paddle device moving up and down, instead of having it be stationary and watching the waves go along, and maybe I'm outside here measuring the velocity of the waves, I'm going to start moving that paddle device. So let's think about what's going to happen here. We've said that the speed of the waves depends on the medium. By moving the paddle device, I'm not changing the properties of the medium in any way, unless I move it up and down so fast it starts heating the water or something like that. But we'll assume we're not doing anything like that. So the waves are just going to keep the peaks of the waves. Imagine the peaks of the waves going out here. As I move the paddle device along, that means I'm generating a new peak before this peak has traveled as far as it normally does. So what happens is the peaks as I move along here are closer together than if the paddle device was just normally stationary like this, generating the peaks that go by. So in other words, generate a peak, it gets to here, and normally the wavelength would be that long if the paddle device is not moving. But in this case, I've moved the paddle device a little bit more over this way as the wave has traveled out. And now I'm generating a new peak right here. And so that distance is shorter just because I'm moving the paddle device, the source of the waves, along. So the peaks going in this direction sort of bunch up a little bit. And actually the peaks, if we extend our tank the other direction as well, the peaks are going to extend out a little bit more. So imagine a paddle device in the middle where I'm generating waves going in both directions. If I don't move the paddle device, everything's the same. If I start moving the paddle device in this way, the peaks are going to be bunched up a little bit more, and over here they're going to be spread out a little bit more. So in this direction, I'm shortening the wavelength a little bit. In this direction, I'm extending the wavelength a little bit. So when I have a moving source, just to emphasize here, no change in wave speed. Okay? There's no change in the wave speed because the medium, properties of the medium are not changing. What is changing is the wavelength. Okay? And we're dealing in just a simple basic case here, leaving out a lot of complicating circumstances. But essentially, here's my wave generator, my paddle device. As it moves this way, the distance between the peaks gets a little shorter, and they get spread out this way. So in this direction, the wavelength is shorter, and it's longer out this direction. Well, remember the relationship we had from part one of our few words about waves? We said the velocity of a wave, the waves we're considering at least, is the wavelength, lambda, times the frequency f. Now, we've just said that we're not changing the properties of the medium, so the velocity of the waves is going to stay the same. What we're changing in this case with a moving source is the wavelength. In this direction, as I move the paddle device along, the peaks are closer together, which means the wavelength is a little shorter. In this direction, away from the paddle device, it's moving away from this direction, peaks are a little bit farther apart. Wavelength is longer. What does that imply about the frequency? If the wavelength is getting shorter, in order for the velocity to remain the same, the frequency has to be higher. Let me do an example. Let's just say this is 24. Say velocity was 24 meters per second, right? And I said the wavelength was 4 meters. Frequency was 6 inverse seconds, really. Some of you may know the units of frequency are hertz. So when we talk about megahertz, that's millions of hertz. So we won't worry about the details here, but just the idea, 4 times 6, 24 obviously. So now I'm saying as a paddle device moves along here, the wavelengths are getting shorter. Let's say they go from 4 to 3. So that means the frequency has to increase. So I'm going to have a situation where it's 3 times 8. That's why I chose the numbers here, so I could do it easily. So 3 times 8 is still 24. Right? So the velocity stays the same. The wavelength has compressed a little bit, gotten shorter, so the frequency has gone up. And whether you realize it or not, you probably have encountered this in real life, or at least seen it in the movies. Think about a train whistle, right? If you have a train whistle and the train is coming towards you, you have sound waves coming toward you from the train whistle. The velocity of the train is a moving source, or the train is a moving source with a certain velocity towards you, the source of the sound waves. As we've been talking about, the velocity of the sound waves toward you does not change. They are still coming towards you at the same rate. They won't get there any faster to you. But because it's a moving source towards you, the movement of the train compresses the wavelengths of the sound out in front of it as it travels away from the front of the train. And that means shorter wavelengths, higher frequency. So that's why when the train whistle coming toward you, you hear it, it's a higher pitch. Then as it passes by you, now you're behind the moving source. Okay, just on my paddle device, I was moving the other direction though. So the paddle device was moving this way. Shorter wavelengths here, longer wavelengths behind it. Same idea for the train whistle, whether it's moving this way or that way. It doesn't really matter. We're pretending it's coming this way. So here comes a train toward you. It's compressing the sound wavelengths in front, which means a higher frequency, higher pitch sound. As it moves by, what you hear, the pitch drops. It goes like that, more or less. And that's because behind the source, the moving source, as it moves away from you, the wavelengths spread out a little bit, meaning that you have a bigger wavelength. Okay, this number becomes bigger. The frequency, therefore, has to be smaller to keep the velocity the same, the whole thing the same. And therefore, you have a lower pitch sound. And some of you, again, may know that this is something called the Doppler effect. Doppler effect. So it's just a little side note. It actually, there is a so-called relativistic Doppler effect. We're not going to get to that in this course. But it is important. The important point here is that wave speed depends on the medium. When you have a moving source, it does not change the speed of the wave through the medium. It changes other things. It changes the wavelength and frequency. Does not change the speed of the waves. And this is important. You may say, well, why are we doing all this with wave stuff? It's important because we mentioned Einstein had two postulates, two principles that he enunciated in his special theory of relativity. One of them was a principle of relativity. The second one was essentially number two here, our number two. He called it the principle of light constancy. And essentially it was that a moving source, there's no change in the wave speed. And light was recognized as a wave. So he said, hey, with a moving source, there's no change in the speed of light. But what then became very interesting was he combined the principle of relativity with his principle of light constancy and got very strange results. And that's where we're heading to in, not quite yet, but we're heading in that direction over the next week or two. So that's why this is so important to understand. A moving source, no change in the wave speed, because it's going to help us understand what Einstein was doing when we get there. Okay, moving source, no change in the wave speed. One other key fact, though, a moving medium. A moving medium, what do we mean by this? Well, again, let's go back to our water tank. So here's our water tank here. And we have our paddle device generating waves flowing down the tank. And we're measuring the velocity of the waves there. And as we just finished saying with our principle number two, if I move the source of the waves through the water, it doesn't change the velocity of the waves. You know, the frequency and wavelength change, but not the velocity. But now let's think of another situation. Here's my paddle device. Here's my tank. And I'm measuring the speed of the waves as they go along. What happens if I move the whole thing? So in other words, the medium is moving as well as the waves. In that case, when I have a moving medium, the velocities do add in a sense. Okay, so I'm measuring, before I set the whole thing in motion, I'm measuring the speed of the waves as they go along here. And then, maybe I have it on rollers or something, on wheels, I start moving the whole thing. And then I measure the speed of the waves going by me. And pretty intuitively, intuition is correct here, you'll see the speed of the waves increase. They'll be going by you at their normal speed, plus the speed that the whole thing is moving by you. So with a moving medium, then the wave speed, we'll just say the wave speed changes as an observer is measuring it. Now, in terms of the medium here, another way to think about this, we've done our water tank example, but it's also the difference between, say, generating waves in a pond or a lake and a flowing river, right? So, or if you're able to set the lake in motion in a sense. So if it's in the lake or pond, again, it's just you generate the waves, they're flowing along here. If you have that same situation in a river, and let's say the river is flowing this way, so I'm generating my waves here, and they're traveling along, but then everything is in motion as well. All the water molecules and everything are flowing this way, and so that adds velocity to the velocity of the waves if I'm on the bank measuring those waves go by. Or, intuitively also, if I'm going upstream, up against the current, right? So I'm watching the device here, maybe on a boat, as it goes up the current, generating waves. The flow current of the water will retard the velocity of the waves trying to go upstream. Again, that's one case where our intuition actually is correct there, that the wave speed will change. If the whole medium is moving, the wave speed will change. Why is this important for our purposes? Because in the next video clip, we're going to talk about something called the luminiferous ether, and that is the supposed medium for light waves. And Einstein actually got rid of it later on. We'll see how that happened. But there are two key experiments that we need to talk about, because one of them, known as the Michelson-Morley experiment, gave one result in terms of how the ether worked and how light waves worked, traveled in the ether. And a second experiment involving something called stellar aberration, stellar meaning stars, and aberration we'll figure out what that means, gave an opposite result, a result that contradicted the Michelson-Morley experiment. And both of them were well understood. And so it was like physicists were just nonplussed. They couldn't figure out, what do we do with this? How do we understand this? And they came up with a number of very innovative ideas, very creative ideas, but it was still a big mess. And they tried and tried and tried, and eventually that was one of Einstein's great triumphs. By attacking it sort of from a different perspective, he was able to show that these things actually were not in contradiction, even though they seem to be. But by coming from a perspective where they're not in contradiction, then you get all kinds of other interesting and weird results. So that's where we're heading with this. These principles are going to be key in understanding these two different results, the Michelson-Morley experiment and stellar aberration, and so we'll be covering those over the next few video clips.